Okay, so we're going to use the product and quotient rules to solve different problems, and when and when not to use them, well, lots of different things. So the first thing asks us to find the derivative of these two functions. Well, if I want to go ahead and use the product rule, I can, and that's just fine. I'm going to need to decide, just make sure I distinguish between the two functions. Okay, so I start off and I say, okay, well, h prime of x, and sorry to be confusing with the concept video that I made earlier, doesn't really matter what the first thing is. It's always the derivative of this, and think of it as first function and second function, so green and blue. So I always start by rewriting the green function, which is going to be 3x minus 2x squared. You then multiply it by the derivative of the second. So the derivative of the second, the derivative of 5 is 0. Derivative of 4 is 4x is 4. So this is just a positive 4. I then add my second function, which is going to be 5 plus 4x. And I multiply that by the derivative of our first function, which the derivative of 3x is 3. The derivative of negative 2x squared is going to be negative 4x. So this is going to be 3 minus 4x. So then I'm going to go through and simplify this whole thing. Well, I got to distribute this 4 to both parts. So I'm going to get 12x minus 8x squared. I then have to FOIL this next part. So I got my first, which is 15. My outside, which is going to be negative 20x. My inside, which is positive 12x. And then my lasts, which is going to be a minus 16x squared. And then just have to combine like terms. So my negative 8x squared and my negative 16x squared makes negative 24x squared. I then have 12x minus 20x plus 12x. You should get a positive 4x there. And then I'm just left with a positive 15. So this should be your answer. It's going to be negative 24x squared plus 4x plus 15. You could have multiplied everything up top beforehand and then just done the power rule. Either of them work just fine. Whatever you're comfortable with doing is fine with me. So find the derivative of 3x squared times the sine of x. Okay, so again, our first function is we're going to call that 3x squared, and our second is going to be the sine of x. So y prime is going to be my first function, which is 3x squared, times the derivative of my second, which is cosine of x. So I'm just going to leave this as cosine of x. Then I add, and I've got the first function, which is the sine of x, times the derivative of my first function, which is going to be 6x. So now, just simplify, no big deal. So I got 3x squared times the cosine of x plus 6x times the sine of x. At this point, you could factor some things out, but it really doesn't make anything any cleaner. You're just going to end up with more terms. So this is actually fine as an answer for me. Okay, so now we got to think about the quotient rule. This is that's why you can't see it. So we've got a rational function. We can't simplify it. We can't do anything with it. So we have to designate these as different functions and think of them separately. So we are going to say that this is our high function, and this is our ho function. So we start off and we say, okay, well, our high function is 5x minus 2. Our ho function, our d high, so the derivative of that is just going to be 5. Because the derivative of 5x is 5, and the derivative of negative 2 is 0. We then have our ho function, which is x squared plus 1. And then we have d ho, which is going to be 2x. Well, now we just have to put them together with our little jingle. Okay, so you remember our little jingle was ho dee hi less hi dee ho over ho ho. So these link, and then you divide by ho ho. The important thing is you start with ho, right? You start with ho, dee hi. Start with the small one in the inside, and you end with the larger one. So we're going to go ahead and put these together. So y prime is going to equal the following. It starts with ho, which is x squared plus 1 times d high, which is 5. We then subtract the converse, which is going to be high d ho. So we get 5x minus 2 times d ho, which is 2x. And we then divide by ho ho, which is x squared plus 1 squared. So at this point, we need to go through and simplify. Sometimes we end up getting things to cancel, but oftentimes we just need to clean it up. And so if we simplify our first term here, we're going to get 5x squared plus 5. Our second term, we got to make sure to do the opposite of everything because we're subtracting. So we get 2x times 5x, which gives us 10x squared. We're subtracting, so we get minus 10x squared. And then we get 2x times negative 2, which is negative 4x, which becomes a positive 4x. And then subtract by x squared plus 1 squared. Now if we continue, if we combine our like terms, we have a 5x squared, we have a negative 10 to make a negative 5x squared. We're left with a positive 4x, positive 5, and we divide by x squared plus 1 squared. There's no way to simplify this any further, so this is our derivative. So we could use this to find the slope of our original function anywhere we want. Now, there are times when you're going to see a quotient and you're going to think, well, why don't I just go ahead and use the quotient rule? Well, you don't always have to. If you think a little smarter, because the quotient rule is kind of lengthy, you can be a little smarter and save yourself some time. So let's look at our first one. So our first function says x squared plus 3x over 6. You'll notice that all of these things have one thing in common, and it's that every denominator has a single term. Okay, it's all got a single term, and this makes things very, very easy. We can think of this as two fractions. We can split this up. This is a fraction that has been combined. We just want to split it back up. So this is going to be x squared over 6. Okay, and then we have our second function, which is going to be a positive 3x over 6. Well, if we went to actually do the derivative of this, it's now a lot easier than it was before. So splitting up the function can allow us to not have to do the quotient rule at times. Now, sometimes you have to, like our previous example. But in this example, we could go through now and do two separate versions of the product rule. And again, if you wanted to see this, this could be written as 1/6 x squared plus 3 over 6 is the same as 1/2 x. So very, very simple way to write it. So B says we've got 5x to the 4th over 8. Well, we worked on this before with our constant multiple rule, but we can, again, split this up. We can think of this as 5/8 out front. And then you're multiplying by x to the 4th over 1. Well, this is the same thing as 5/8 x to the 4th. So again, something that we could easily evaluate using the power rule. C, this one looks a little ugly, so we got negative 3 times 3x minus 2x squared all over 7x. So just because this has an x in it doesn't mean anything, right? We just have to simplify and separate stuff. Well, I'm going to multiply the top out first. I'm going to get negative 9x plus 6x squared all over 7x. So, like the previous examples, we're going to split this up. We're going to say this is going to be negative 9x over 7x. And we're going to say that this is positive 6x squared over 7x. Well, we can simplify this and make this very, very manageable and very, very easy for us. Well, we've got an x on top and bottom, so those actually cancel. So this actually just ends up being a negative 9 over 7. We then have an x on bottom and top. We take away 1 from the top, we take away 1 from the bottom, and we're left with a positive 6x over 7, which we can think of as positive 6/7 x. So overall, this derivative is very, very easy to find. It would have been a big pain to have to do this with the quotient rule, and then you would have had to do a lot of simplification to get to a very, very easy one to take the derivative of right here. So we haven't taken the derivative. None of these are derivatives. These are just simplified versions that we can make instead of applying the quotient rule. Now we can do the product rule to this problem. And then lastly, we've got d, and we have that to be 9 over 5x squared. Well, we could call this the same as 9 over 5 times 1 over x squared, which we're going to see this is going to be 9/5, okay, times 1 over x squared, which is the same thing as x to the negative 2. So this answer down here, it's not a derivative. It's not a derivative yet, but this is just a different way to write it so that we can find a derivative without having to go through the hassle of the quotient rule. Okay, so let's look at some of those special derivatives that we worked on earlier to find these. So the derivative of tangent, we said, was secant tangent, or secant squared, excuse me. So if I found the derivative of y here, I first find the derivative of x. The derivative of x is just going to be 1. I then subtract away the derivative of tangent, which is secant squared of x. That's it. That's all you have to do. And for b, we now have x secant x. So this is a little more complicated. We have a first function, and we have a second function, and then there's a product. So we have to do the product rule. And there's no escaping it. So I always start off and say, okay, we start with the first function times the derivative of the second, which is secant x tangent x. We then always add our second function, which is secant x, times the derivative of our first function, which is 1. So we're left with y prime equaling x secant x tangent x plus secant x, which in this case, we could leave it this way or factor. You could write it as secant x times x tangent x plus 1. If that makes it easier for you, then that's fine. Both of those could work just fine. I mean, you end up with 2 terms at minimum anyway. Our last example has to do with our higher order derivatives, our position, velocity, and acceleration. So it says, because the moon has no atmosphere, a falling object on the moon encounters no air resistance. In 1971, astronaut David Scott demonstrated that a feather and a hammer fall at the same rate on the moon. The position function for each of the following objects is given by s of t equaling negative 0.81 t squared plus 2, where position is the height in meters and t is the time in seconds. What is the ratio of Earth's gravitational force to the moon's? Okay, well, the acceleration due to gravity on Earth, so the acceleration due to gravity on Earth is negative 32, that's feet per second. I apologize. It's negative 9.8 meters per second squared. Okay, so we are constantly accelerating at negative 9 0.8 meters per second squared towards the Earth. So let's see what we're at on the moon. So first off, if we have position, we can find velocity. So the derivative of position gives us velocity. So let's take the derivative of the function on top. We'll get 2 times negative 0.81, which will give us negative 1.62 t plus 0. So that is our function for velocity. So as time goes down, you are gaining or losing, you're going down 1.62 more meters per second than you were before. Now, if we want to find acceleration, we need to do the second derivative, which is the first derivative of velocity, which gives us our acceleration. So this is going to be the second derivative here. So our second derivative is just negative 1.62. So it asks, what is the ratio of Earth's gravitational force to the moon's? So if we do this, we would have, over here, we would have negative 9.8 divided by negative 1.62. Or, let me write this another way. Negative 9.8 divided by negative 1.62. This is pretty much a sixth, but I can prove that to you if I actually go through the process of dividing these. So for the sake of argument, because they're both negative, I'm just going to go ahead and do 9.8 divided by 1.62. So in this case, 1 goes, we'll say 16 goes into 98. It goes in 6 times. So 6 times this is going to be 972. I think, yep. And then we're left with this, so 80. This doesn't go in, so we get 8.0. We then add a 0 to it. This goes in 4 times. So 4 times this would be 648, which that gives us 152, which again doesn't go in. 162 doesn't go into that. So we end up about 6 times as much, right? Our gravity is over 6 times that of the moon's. But the main thing that I want you to get from this is not all this crap over here. It's mainly that if we have a position function, ooh, wow, and it has now disappeared. If we have a position function, we can use that to find our velocity function, and we can use that to find our acceleration function.